In this lesson, we're going to examine scientific notation. Specifically, you should be able to answer the question, how do I convert between scientific and standard notation? So let's establish what scientific notation is. First of all, it's a shorthand for writing very large or very small numbers. It's written in the form of a times 10 to the nth power. There are some conditions on both a and n. A must be a value that is greater than or equal to 1 but less than 10. So it could be something like 8.3, but it could not be 27.4 because that's larger than 10. N is an integer. So no fractions or decimals, but negative and positive whole numbers are fine. So let's decide if these following examples are indeed examples or if they are non-examples of scientific notation. So 12.45 times 10 to the fourth. It looks like it at first glance, but this is a non-example because 12.45 is greater than 10. This next one, 9.5 times 10 to the negative fourth, fits the conditions. A is between 1 and 10, and the power of 10 is an integer. 0.87 times 10 cubed, this would be a non-example because the a value is too small. Okay. Another common one that sometimes throws kids off would be if you had something like 2.45 plus 10 to the sixth. On a standardized test, sometimes they sneak in values like this because it's addition here, not multiplication. Okay, now let's explore what multiplying by powers of 10 actually do to a problem. So I'm going to start out here on the positive side. If I have 1.35 times 10, all that does is it's multiplying by 10, so it shifts your decimal point 1 to the right. It becomes 13.5. 10 squared is actually 100, so when I multiply by 100, it shifts the decimal point 2 places to the right to become 135. 10 cubed is actually 1,000, so I shift it 3 to the right, 135, and I end up putting a 0 on the end for 1,350. So multiplying by a positive power of 10 moves it in the positive direction on the number line. Multiplying by a negative exponent, well, we just learned that negative exponents are actually fractions. So if I do 2.5 times 1/10, I'm actually dividing by a power of 10, so it's getting smaller. I end up shifting the decimal point in the negative direction on the number line. It becomes 0.25. If I multiply by 10 to the negative second, I shift 2 place values to the right, which causes me to put 0 to become 0.025, or 25 thousandths. In the next one, I'm going to shift 3 place values to the left to become 25 10,000ths, or 0.0025. Now, one of the things that you'll notice is it's much easier to read numbers in scientific notation than standard notation. So standard notation here, this is just the normal way that we've always written numbers. So in the next example, it says write each number in standard and scientific notation. So 2 million, think about how many zeros do you need for 2 million? This would be 2,000. Here's 2 million. So changing this to scientific notation, what I do is I take the non-zero point part of the number, the 2, and I think about, well, where would I put that decimal point, and then count how many place values to get it back to where it was. So that would be 1, 2, 3, 4, 5, 6. So times 10 to the 6th power. 5 thousandths, this would be the tenths, hundredths, and thousandths place. Now to write that in scientific notation, I take the non-zero part, the 5, and then I think, well, where would I move it, the decimal point, to get it back to where it was? It'd be 1, 2, 3 to the left, so times 10 to the negative third. Okay. Now we're going to quickly write a few of these numbers in scientific notation. Again, your a must be between 1 and 10, so the non-zero part of this number is 34. But 34 is too large, so it would have to be 3.5. 3.4. The decimal point would have to go between the 3 and the 4, and then I count how many places to get it back to where it originally was. That'd be 1, 2, 3, 4, 5, 6, 7, 8. So times 10 to the 8th. For number 4, 709 is the non-zero part, and the decimal point would have to be between the 7 and the 0. Count how many place values you have to move it to get it back to where it was. Shift the decimal point 1, 2, 3, 4 places in the negative direction. Now, one of the things you can do is always toss this in your calculator and make sure that how you are expressing the number in scientific notation agrees with the standard form. Number 5, try this one. It would be 2.3 times 10, and count your place values. If you're placing it here, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2.3 times 10 to the 10th. Number 6, now this is a tiny number, so my brain starts thinking, well, when they're small numbers, typically it's multiplied by a negative exponent. So I count 1, 2, 3 to the left would be times 10 to the negative third. Try 7 and 8 and pause the video, and then we'll see if we agree. Here are my answers to 7 and 8. Now, 9 and 10, the common thing that kids will do here is they'll change these both to standard form, moving the decimal point 6 places to the right, which would cause 5 more zeros to be placed on the end, making it 34,800,000. However, you have to change this back to scientific. So it'd be 3.48 times 10 to the 1, 2, 3, 4, 5, 6, 7, 7th place. But there's an easier way to do this. So I'm going to explain this a much quicker way. So originally, this is not in scientific notation, and here's the issue. 34.8 is too large. It needs to be 3.48, the decimal in between the 3 and the 4. So here's what I think. If I shift this decimal point 1 to the right, I've changed the value. I've actually divided by 10. So I need to compensate by shifting the exponent in the opposite direction 1 unit by multiplying by 10. So it would become 10 to the 7th. That's the easiest way, in my opinion, to do this. Shift it 1 to the left, divided by 10, shift the exponent 1 to the right on the number line, multiply by 10. I'm going to do this next one the same way. This time, I need to shift the decimal point 1 to the right, which means on the number line I have to shift -4, 1 to the left, the opposite direction. So it would be times 10 to the -5th. Again, if you type both of these into your calculator, you'll see that they produce the same value, so you'll know that they are equivalent. Final example is I'm asking you to order these numbers from least to greatest. Most kids would pick up their calculator and start changing these to standard form. You can certainly do that, but what I notice is the majority of them are already in scientific. So instead, I'm going to change 2.805 to scientific and have them all be in scientific form. So this would be 2.805 times 10 to the third. So what I look at is, since they're all, I'm going to line them up vertically, it'd be easier on your eyes to see. Times 10 to the 5th. 3.2 times 10 to the 4th, and 3.024 times 10 to the 2nd. So here's what I see. Since they all are between 1 and 10 for their a value, I'm just going to look at the exponent that's smallest. It's 10 squared. So this value here is the smallest. 3.024 times 10 squared is less than. The next value would be the cubed one, 2.805 times 10 to the third. Now I'm going to write that back in its original form. It's good practice is always put your numbers in the form they were expressed in. Now, to the 4th power, I have 2 of them. So then I'm going to look at the a values. 2.81 is smaller, so that one's next. Is less than 3.2 times 10 to the 4th, which is then less than, I'm running out of space here, the 2.8 2.08 times 10 to the fifth, and I'm going to write that underneath here. Hopefully you budgeted for more room on your paper. So that's how you write numbers in scientific notation, and hopefully you see the advantage. They're much quicker to read. And in our next lesson, you'll see how you can perform operations with numbers in scientific notation.